Into the classroom one day and you see a setup just like this on a table. There's a ring stand, a clamp. Tied to the clamp is a string, and then hanging straight down from that string is a mass, a weight. I think you could all recognize this right away as a pendulum system, and it's possible for us to make some interesting observations about the pendulum system. We can observe very simple things such as that there's string, hanging straight down on the string is a mass. But the most interesting thing we could observe is this behavior, that if we deviate the string, deviate the system away from its resting point and let it go, it starts to move back and forth in a rhythmic motion. We call this an oscillation, oscillatory motion or harmonic motion because it has a rhythm to it. And one complete cycle, forward, back to where it started, that is called one oscillation. Forward, back, that's one oscillation. And then we could start asking some really interesting questions about this system. We could try to find some relationships. We could see how we can change things about the system. See what we could measure about the system. So what are some things that we could measure? Well, very clearly, we could take the ruler and we could measure the length of the string. We could maybe measure the height of the pendulum above the ground. There's a protractor set up here, so we could use that to measure what we refer to as the angle of release. It's kind of like how high are you swinging the pendulum and then dropping it, letting it go. So we could measure the angle of release with the protractor. What else can we measure? We can measure the mass of this thing, the length of the string, I think I said already. So there's lots of objective measurements that we could take about the system. And it's possible that after exploring the system, after making our observations, we could start to ask some questions, find relationships. One of the most interesting questions I think we could ask would be, how can we change the amount of time it takes for the pendulum to complete one oscillation? How can we change how much time it takes for the pendulum to complete one oscillation? Remember, one oscillation is one forward and back motion. So there's one oscillation, there's one, there's one. Is it possible for us to change the amount of time that takes? And if so, how can we do it? Is there a relationship between that time and the length of the string? Is there a relationship between that time and the mass of the pendulum bob down here? Is there a relationship between that time and how far we drop the pendulum, the angle of release? So we could ask these questions and try to find relationships and start designing an experiment. An experiment is a controlled study where you are attempting to find an answer to a question that you've asked. Another way of putting it is that an experiment is hypothesis testing. A hypothesis is, you guys have probably heard it defined as an educated guess, but really a hypothesis is just a proposed prediction or relationship based on previous observations about what you think might happen. So remember, the question that we're asking right now is, how can we change the amount of time it takes for the pendulum to swing back and forth one time? That back and forth swing, as I said earlier, is known as an oscillation, one complete back and forth cycle of harmonic motion. And the amount of time it takes for the system to complete one oscillation is known as the period, the time required for a harmonic system to complete one full oscillation. So this is what we're trying to measure. This is what we're trying to change. And our question is, how can we change the period of a pendulum system? And from our previous observations, we recognize that we can change a lot of things about this. We could change the mass, we could change the length of the string, the angle of release. If we could go to different planets, we could change the amount of gravity, the gravitational field strength that this pendulum is subjected to. We're not going to do that. So, From this question, we can form a hypothesis, an educated guess, a predicted relationship. Typically, hypotheses take the form of an if-then statement. So we could say something like this. If we increase the angle of release, then the period will get longer. Or if we increase the length of the string, then the period will get longer, etc., etc. So we can form several different hypotheses, and then we can design an experiment to test the hypotheses. So remember, we're saying that experimentation can be defined as hypothesis testing. We're trying to see which hypothesis is correct. So if we change the length of the string, then the period will get longer. If we change the mass, then the period will get longer. If we change the angle of release, then the period will get longer. So these are the hypotheses that we're going to test. Now, how do you think we should go about designing our experiment in order to test these hypotheses well? In order to get good data, good results, good measurements that we can trust, that we know are valid? Well, some general rules of thumb are that we should only test one hypothesis at a time. In other words, we should only change one variable at a time. Here's an incredibly important word, variable. Everything that we mentioned up here in our if-then statements are variables. Variables are things that we as the experimenters can change, or that may change as a result. So look back up here and see if you can see what the variables are. The angle of release, that's a variable that we are going to change. The length of the string, that's a variable that we can change. The mass of the pendulum bob, that is a variable that we can change. What variable are we hoping to see change in as a response? The period, how long it takes to complete one oscillation. So we can only change one variable at a time and measure one other variable at a time. Those are called the independent and the dependent variables. So we can only test one independent variable at a time, only measure one dependent variable at a time. All other variables must remain constant. So let's talk about these phrases I've just thrown out there. Independent variable, those are the variables that the experimenter changes. So what are we choosing to change? The angle of release, there's an independent variable. The length of the string, there's an independent variable. And the mass of the pendulum bob, those are our independent variables. How do you think I'm going to define the term dependent variable? Think about the word dependent. That's right, it is the variable that may change in response to the independent variable change. So here's the key term, in response to. In other words, we could say that the dependent variable is the variable which depends upon the independent variable change. So two different ways to define dependent variable. So independent variable is what we're changing. The dependent variable over here is always going to be the period, what we're measuring and hoping to see a change in response to these independent variables. If we increase the angle of release, in the period as a response may get longer. That's our educated guess based on observations. That's our if-then statement. That's our hypothesis that our experiment is going to test. Every other variable must remain constant. In order to have an experiment and set it up so that we can trust the results are valid, we have got to only test one variable at a time and keep every other variable constant. We have to have a controlled experiment. So we're actually doing 3 experiments here. We're going to collect some data. We're testing these 3 hypotheses. How does the angle of release relate to the period? How does the length of the string relate to the period? How does the mass of the pendulum bob relate to the period? I'm going to show you guys on my little simulator here how I would set up these experiments. And then I'm gonna collect some data and kind of fill in these tables. And then I'll teach you a little bit about analyzing the data and trying to find a good relationship. All right. Okay, so the first hypothesis that we're going to test and get data for is the angle of release. So I have got to keep the mass constant throughout all these trials. I got to keep the length of the string constant throughout these trials of angle of release. So I'm not going to touch those at all. Instead, I'm just simply going to change the angle at which I release the pendulum each time. And from my experience, I know that this experiment works best if we hold to small changes, to small angles. Let's say less than 12, why not? 4 and 2, I wonder if I can even get 2 on here. I can. Okay, so those are angles of release. Should I measure and perform an experimental trial with the 12-degree angle of release just one time? Let that swing down, time it, and then just take that data and get a single piece of data here? No, what I need to do is take an average, because averages will help smooth out any error. There's going to be a lot of error here, and you always have got to think about error whenever you're designing an experiment. Where do you think the biggest error could come from? I think the biggest potential error we have is in my reaction time and stopping and starting the stopwatch over here. So it's going to be a little bit tricky to do this, but I'm going to do my best. So let's do a trial at 12 degrees. Remember, I'm using the definition of oscillation as one complete forward and back cycle. I'm not going to be able to come down here and get it on the first one, so I'm going to do the second oscillation. All right, here we go. All right, looks like 1.79 seconds. So I'm going to write that down, and then I'm going to get another trial. So I can have lots of data to smooth out any error. All right, here we go. You can see here that I found the average of those, so I'm going to get rid of that individual data, and there it is, 1.66 seconds for that angle of release, the average of 3 trials which I took in an attempt to smooth out and correct for any error. I'm going to go ahead and get the rest of the data. You guys can sit back. If you would like to do this, you can find it at fet.colorado.edu. And you can find the pendulum simulation, play around with it, take your own data if you wish. I'll be back.